We now move into the field of modeling control systems. This is the first step in using physics and math to describe, predict, analyze, and optimize control systems. In this introductory presentation, we will not delve into the math and physics, which would make up modern control theory. We will, however, return to it before the end of the course. It is the use of math and physics that can be daunting or exciting depending on your passion for math. We will try to focus on the practical applications and won't go too far into the math weeds. If math and physics are your passion, then be aware that there is a whole branch of engineering awaiting you, and many good texts and videos available. So let's look at transfer functions. Physically, a control system is a collection of components and circuits connected together to perform a useful function. Each component in the system converts energy from one form to another. For example, we might think of a temperature sensor as converting degrees to volts, or a motor as converting volts to revolutions per minute. To describe the performance of the entire control system, we must have some common language so that we can calculate the combined effects of the different components in the system. This need is behind the transfer function concept. A transfer function is a mathematical relationship between the input and the output of a control system component. Specifically, the transfer function is defined as the output divided by the input. It's expressed as shown on the screen. Technically, the transfer function must describe both the time-dependent and the steady-state characteristics of a component. For example, a motor may have an initial surge of current that levels off at a lower steady-state value. The mathematics necessary to account for the time-dependent performance is beyond the scope of this course. In this course, we will consider only the steady-state values of the transfer function, which is sometimes called simply the gain, expressed as shown. In this example, a potentiometer is used as a position sensor. This is an example of a component of a control system, not the entire system. In this case, it is the transfer function of a sensor. The pot is configured in such a way that 0 degrees of rotation yields 0 volts, and 300 degrees yields 10 volts. Find the transfer function of the pot. The solution is as follows. The transfer function is the output divided by the input. In this case, the output is volts. The input to the pot is position in degrees. Our transfer formula is output over input, which is 10 volts divided by 300 degrees, or 0.033 volts per degree. The transfer function of a component is an extremely useful number. It allows you to calculate the output of a component if you know the input. The procedure is simply to multiply the transfer function by the input. For a temperature measuring sensor, the input is temperature and the output is voltage. The sensor transfer function is given as 0.01 volts per degree. Find the sensor output voltage if the temperature is 600 degrees Fahrenheit. Again, taking our formula, TF equals output over input, we can rearrange it as the output equals input times the transfer function or gain. Plugging the numbers in gives a value of 6 volts. A good habit is to check the units. In this case, degrees times volts divided by degrees leaves an answer in volts, which is what we expected. As mentioned previously, transfer functions can be used to analyze an entire system of components. One common situation involves a series of components where the output of one component becomes the input to the next, and each component has its own transfer function. Diagram A shows the block diagram for this situation. This diagram can be reduced to a single block, diagram B, which is the product of all the individual transfer functions. Mathematically, it can be shown as follows, where such subscripts have the values as shown. This equation is for open loop systems only. If there is a feedback path, as shown in this diagram, then the overall system gain can be calculated as follows. Transfer function equals output over input, which works out to be G over 1 plus GH, where G is the total gain in the forward path and H is the total gain of the feedback path. You should do the algebra yourself to see that this is indeed the case. Consider the system shown. It consists of an electric motor driving a gear train, which is driving a winch. Each component has its own characteristics. The motor, under these conditions, turns at 100 RPM for each volt applied. Note this is not how motors work, so assume that the motor is driven by a variable speed drive with a variable voltage input, which outputs a frequency based on the voltage at its reference input. The output shaft of the gear train rotates at 1/2 of the motor speed, and the winch with a 3-inch shaft circumference converts the rotary motion RPM to a linear speed. The individual transfer functions are given as shown. This means the system has a velocity of 150 inches per minute for every volt at the input. For example, if the input setting was 2 volts, the velocity would be 300 inches per minute. Again, check the units to see that we have done the maths correctly. We have shown that the transfer function of the complete system is 150 inches per minute per volt. Knowing this value, we can calculate the system output for any system input. For example, if the input to the system is 12 volts, the output speed of the winch is 1,800 inches per minute. Again, check the units to make sure that they make sense. This brings our presentation on transfer functions to an end. Keep going, doing well.